See, chapter 13. I guess this is like last time, nonpolar pi bonds where we add an electrophile. This time we're going to do the similar reactions, but using different transition state, cyclic transition states. All right. Well, that's just a list of the topics. Here we go. The chapter 12, we worked through these electrophilic additions by way of carbocation formation. The problem with carbocation formation is the generation of a carbocation is very unstable because the carbon doesn't have a complete octet. That's not to say that it doesn't happen, but there is a better way. If the electrophilic atom that's part of the electrophile has a lone pair of electrons, then addition can take place without losing the octet. And that's where the cyclic comes in. We either form an epoxide usually or a three-membered carbon ring, depending on the reagent. And we'll look at that in the next slide. I mentioned that already. These bonds are coordinate covalent bonds. In other words, the electrophile has a pair of electrons. It forms a bond, and the attacked species forms a bond with its pair, and that's usually from a pi bond. So the pi bond donates its pair, and the electrophile donates its pair to form the other bond. Let's see. That's a good point. When we get to the next slide, we're going to see the hybridization on the carbons change from sp2 to sp3. Okay, here's what it looks like in a generic form. The top illustration is what we saw last week in chapter 12, where we had a Bronsted acid. The pi electrons attacked the hydrogen and formed a bond with it, but that left one of the carbons, the other carbon, deficient, your carbocation. Whereas if we have an electrophile that has a lone pair available, then we can form a bond with one of the carbons, and the pi bonds form the second bond with that electrophile, and we get the ring. And that ring is more stable than carbocations are, because all the atoms retain their octets. All right. Since this attack occurs from one side or the other, it can attack from the E side or the Z side, then the arrangement of those groups that are attached to the double bond retain their relative positions. So in this example, if we attack from the top, then the R2 and R4 are pointing toward us. And if it attacks from the bottom, the R2 and the R4 are still pointing toward us, and they're on the same side as they were before. All right. Now this presents a problem if the attacking species is chiral, or the attacked species is chiral. Then we get a mixture of stereoisomers as products. Since we can attack from both sides, we get a whole mixture of stereoisomers. Racemic mixtures will develop if the alkene is achiral. Then attacking from one side or the other will give you an equal 50-50% of each of the enantiomers, and that makes a racemic mixture, which is I can't even remember. My mind's gone blank again. They both rotate. One rotates the wrong optical rotation, excuse me. One rotates one direction, one rotates the other, and they're equal amounts, so they cancel out. And you get a non-optical mixture. All right, so one of the ways to form a 3-carbon ring on your alkene is to use what's called a carbene. A carbene is a carbon that's attached to some other groups, usually other carbon groups. And it has a lone pair here. Now, obviously, this is going to be very, very reactive. But the nice thing about it is this carbon has a 0 formal charge. Even though it lacks the carbene lacks an octet, that makes it electrophilic. Right? It doesn't have its octet, so it's looking for electrons. But it's also a formal charge of 0. Right? Remember how we calculate formal charge. What are the valence electrons for carbon? Only 4, right? 4. Okay. Then we have 1 here, we have 1 here, and 2 there. That's 4. That's 0. So that carbon is neutral. Okay, the problem with using the carbene is you have to make it in the reaction mixture itself. To go on. It won't snap. What's wrong with this thing? There we go. Okay, example. For this particular compound, the only available double bond for reaction is the one that's sticking out there in the top, because the others are phenyl rings. They're not reactive. Okay, so we're going to form a carbene from this azide, the methyl azide molecule. And all we have to do is hit it with light. Probably blue light or ultraviolet light will work. And it forms the carbene in the reaction mixture. All right, how does it do that? The diazomethane, sorry. My mistake. And it forms a cyclopropane ring. So the light breaks that weak bond between the nitrogen and the carbon and forms your carbene. And then the carbene is free to form that ring. Now, this happens, like say, concertedly. In other words, both bonds form at the same time. So really, it doesn't matter whether we're showing it attacking the more substituted carbon, right? The tertiary carbon, which is probably correct. It's going to be the more positively charged, or electron deficient, I should say. And then we get that carbon ring. So we know what we know what these rings are good for because they are strained and they're very reactive. So once you form those, then you can do things with them. Just a word of caution, diazomethane is explosive. I think the Nazis used to use it in their rocket plane. And they killed a bunch of technicians doing it too. Okay. Yeah, it doesn't take much energy to break that bond. So this is a good choice if you don't have any other choices. I think we're going to be given some other choices here in a second. But this is to illustrate the point that you do have to form the carbene in situ. All right. Here's another possibility that's a little safer. Only in this case, we're not forming the 3-carbon ring, we're forming an epoxide. And sometimes that's all you need. But if we form this 3-membered ring with oxygen, this is a very, I should say, the reaction conditions are mild. Let's put it that way. And if we use this metachloroperbenzoic acid, here's the way that naming convention comes out. There's your benzene, there's your chlorine, and there's your perbenzoic. This would be benzoic acid. This would be meta. I remember ortho would be chlorine right here. Meta is 1 carbon removed, and para is opposite. So this is metachloro, perbenzoic. And it's perbenzoic because we have a peroxide built into the benzoic acid side of the molecule. All right. So when this reaction occurs, it depends. We're going to look at it in more detail in just a minute, but it depends on what type of molecule is being attacked. These cyclic enes tend to give us just one product. But the alkenes themselves, the non-cyclics, the alkenes, they give us a mixture of isomers. And one of the products is metachlorobenzoic acid. So we borrow one of those oxygens and leave the hydrogen behind. And is one way to look at it. I don't think that's the mechanism, though. And the MCPBA is not explosive. One advantage. Notice the difference in the reaction conditions. For the cyclopentene, we're using a base and water, sodium bicarbonate and water. Whereas with the alkene, the trans-butene, we're using a non-protic solvent, the dichloromethane. All right. So here's what the proposed mechanism looks like. My picture's covering up some of it, and I can't get rid of that for you. But the reaction is concerted. In other words, there's been research done on it, and all this happens at one time, at the same time, in a single step. That way, we avoid carbocation formation. If you don't form the carbocation, then the likelihood of any rearrangements would be nil. Here's the problem. Look, take a close look at that picture. What's wrong with that picture as for a mechanism? It's been too long ago, hadn't it? It's got 4 curved arrows. Remember? We're supposed to be limited to 3, unless we have no other option. And I think that's the problem here. If it's going to be concerted, we have to have 4 arrows. Okay. Um, the so there's hydrogen bonding going on here, and that's part of the the requirements for this perbenzoic acid to work, is that these are all sigma bonds, so they could rotate, and we rotate that farthest hydrogen around, and it hydrogen bonds with its carbonyl oxygen. And what that does is that sticks that oxygen out there and makes it available with its lone pairs to be transferred to the alkene. And when that happens, the bond between the hydrogen and the oxygen breaks, and we've already got a hydrogen bond forming with the alkene. So it forms the double bond, and the pair of electrons that are left behind when the oxygen breaks with its neighbor oxygen create a carbonyl with the other oxygen. So if you just look at the reaction itself, it looks like the carbonyl wasn't touched, but actually the carbonyl switches positions between the 2 oxygens. And since the sigma bond is between the carbon and the phenyl ring, it really doesn't matter. It's just going to rotate around. It looks the same no matter which direction you approach. Okay, so now what we have formed is an epoxide. Let's see. I think we've already covered those topics, and the printing's too small anyway. It does produce stereoisomers as a consequence. Now, we just show one of them here, but the other one, the other epoxide, will form if the attack is from below rather than from above the alkene. Here's another way to think. This is a mechanistic trick that simplifies the reaction so that we can hopefully rationalize how that oxygen forms the epoxide across the alkene. And that is to view the oxygen as the reacting species independent of the metachloroperbenzoic acid. When we do that, we give that oxygen 3 pairs of electrons around it, right? Which means it's deficient. It needs another pair. So it gets that pair of, oops. Now's a good time to open that bottle. The pi bond electrons now supply the need for the oxygen's deficiency, and in the process forms a bond with one of the carbons. And now that the carbon is deficient, the other carbon is deficient, it takes one of those lone pairs from the oxygen and forms the epoxide. So like I said in the very first slide, one coordinate bond forms with a carbon and oxygen from the pi electrons, both of them. That's a coordinate covalent bond. And then the other coordinate covalent bond forms from the pair of electrons from the oxygen and the opposite carbon. That's just a convenient way to visualize. All right. What are the missing compounds, A, B, and C? Right. Well, we know that if we, in fact, has anybody looked at your the second exam? In my comments, there were a couple in there that just didn't click, and I saw where it was uh, confusing a couple of you. So um, wherever possible, I give you credit for them. But one of them was where we had this alcohol that was in concentrated hydrochloric acid with heat. And what that would do is, rather than form the alkene, that would just chlorinate the molecule because the hydroxide would be protonated. Now it makes water a good leaving group, and you nucleophilic attack that carbon with the chlorine that's left behind. So that I think that was a bad question to put hydrochloric acid in there. It should have been sulfuric or phosphoric like this one. Now, if you do use phosphoric, then you form the double bond, and you're going to get a cyclohexene. That's A is going to be the cyclohexene. And then what forms from the cyclohexene with the MCPBA in dichloromethane is the epoxide. B is going to be the epoxide. And then what happens when you attack it with a base and water? I had a roll going there, and I kind of hit a roadblock. So let me see. Okay, I'm right on the first one. Second one forms the epoxide. Oh, okay. And then you now you have a diol as a consequence. So we went through all that trouble to go from a cyclohexanol to a cyclohexane diol. Cyclohexane 1,2-diol. And this will also, we know from epoxide reactions that we've seen in previous chapters that we're going to get a mixture. We're going to get the enantiomer plus the one that's shown. Just depends on which side it's attacked. I think what that does, doesn't that work through a carbocation? I have to go back and look. All right. What if we have an electrophilic addition across another double bond, the cyclohexene, use bromine in a non-protic solvent? And that makes that eliminates the possibility of surrounding that bromine with water molecules or any other protic solvents, and negating its ability to attack the cyclohexene. So when it does that, we get the possibility to form two different isomers. Well, actually, it doesn't matter. Yeah, it doesn't matter because all you got to do is flip the molecule over. No, they're non-superimposable. Those are enantiomers. My mistake. So we've looked at this in previous chapters. We can add molecular chlorine or molecular bromine across an alkene to produce a three-membered ring. And that makes it now reactive for adding the second bromine. And we're going to look at the mechanism next. But unfortunately, the intermediate is quite unstable. All right, so this is what it looks like when we approach that double bond. The bromine is a nonpolar molecule, dibromine. But as it approaches those pi electrons, they push electrons in the dibromine away, and they make the approaching side bromine electron poor. All right. So what does that get us? Well, as it approaches the pi bond, now the pi electrons can supply the need that nearest bromine has created by approaching the pi electrons. So they're self-reinforcing, in other words. And now we can form that, we can form a three-membered ring, and we call it the bromonium ion, because the bromine now is positively charged. It lost a pair of electrons to the bromine, the leaving group. So bromine is the attacking group and bromine's the leaving group. Now we have that very reactive bromonium ion. And now the bromine, the bromide ion, can attack either one of those carbons. So that's why we get a mixture of enantiomers. It can attack the carbon on the left or the carbon on the right, and whichever one it does, it gives us an anti-arrangement of bromines across that double bond. All right, so what that statement is telling us is that to account for the stereochemistry of the reaction, the mechanism cannot proceed through a carbocation. Otherwise, both syn and anti-addition would take place, and we'd have bromine on both sides of the double bond. So if it's always going to be an anti-attack, then we have to use the bromonium three-membered ring in order to explain it. So this is a case where it's logical rather than experimental. Okay, and we know that for an SN2 reaction, the attack has to come opposite to the leaving group. We've seen that in past mechanisms. All right, let's see. We got another one coming at us. Let's see. What predict the products of the reaction shown here? Do you expect the product mixture to be, optically active? Okay. Is that molecule optically active to begin with? If we look at it, yeah, it has a chiral center, doesn't it? The alpha carbon attached to the oxygen has 4 different groups on it. So that it's a chiral reactant. We're going to hit it with bromine, and what we're expecting is for the bromine to form the bromonium ion across that double bond and add bromine in the anti-positions. So it'll either be one above, one below, or toward the back and front, or toward the front and back. So we should get 2 isomers out of this reaction. Okay. We know what reaction takes place. And are the product's molecules chiral? Is each optically active? And how are the product molecules related? All right, so we should expect to get both of those products, bromine facing forward, bromine back, or the opposite. Okay. Each of the product molecules is chiral. Therefore, they should be optically active. But the product molecules are diastereomers. Why? Because the bromines are opposite to one another on each of the molecules, but that methyl group is still pointing out, right? It's not pointing back on one, so you don't get an equal mix of front and back. That makes them diastereomers. And Consequently, they're going to be formed in unequal amounts, and the product should be optically active. Simply because they're formed in unequal amounts, then the product will be optically active. If they were formed in equal amounts, right, they would be a racemic mixture. All right. Now, what happens in this case? We've switched from bromine to chlorine now, right? We didn't have chlorine on the previous. No, that was bromine. Okay, so we switched to chlorine, and we can do the same thing with chlorine across a double bond, form the chloronium ion. um, oh, I didn't know that. Um, except for the fact that my twos are not subscripted. I got to fix that. So fluorine and iodine will also react with alkenes. Oh, okay. That's a good reason not to use fluorine. It reacts explosively with alkenes. What about iodine? Oh, it's energetically unfavorable. Okay. The reaction occurs, it probably just takes it from months to years to complete the reaction. So we're stuck with chlorine and bromine. Okay. Um, so we're going to get anti-addition of chlorine across that bond, but we should get um, chlorine on the top chlorine facing back and the bottom chlorine facing forwards. But what's the difference? If you rotate the molecule around, it's the same molecule. This is known as a meso. Um, and meso simply means achiral overall. You may have chiral centers, but the overall molecule is achiral and it does not produce optical rotation. Okay, we can get addition of bromine across alkynes also. If we limit the amount of bromine available to one equivalent and give it enough time in dichloromethane, then you should get bromine added across either in the, well, we're going to, in this case, we're going to get Z or E configurations. And that's simply because when you add bromine, just one equivalent of bromine across that triple bond, you've still got a double bond to deal with. So you have the possibility for both the E and the Z isomers. But if you use bromine in excess, it's going to go ahead and brominate the alkene that's left over. And now it's not it doesn't have isomers. Okay, let's see. Yeah, we already said that. All right. So why is that? Notice that you may be puzzling why we get E and Z isomers because that wasn't the case for the alkenes. That's because we're not working through a bromonium ion anymore. The bromonium ion is not stable with the alkyne because the sp2 hybridized carbon atoms would be too highly strained in the ring. And those are the only two carbons that are shown. Now they're sp2 hybridized. They were sp hybridized. Now they're sp2 hybridized. And in the bromonium ion, as before, we had sp3 hybridized carbons, and that's more stability. sp2 hybridized carbons are not stable enough. So we've got to work through a carbocation to get where we're going. And since we create a carbocation, then we can attack from either side, and that gives us both the Z and the E isomers. Okay. What's a halohydrin? Well, it's a halogen in water. The formation actually, though, is a halogen and a hydroxyl across the double bond. All we need to do is make water the solvent, and now we get a mix of isomers where you have bromine on one carbon, hydroxyl on the other. Bromohydrin, chlorohydrin in the bottom example. This is what the mechanism looks like. We can work through a bromonium here, or a chloronium, as the case may be. And once you form the bromonium ion, now the water will attack one of the carbons. It could attack either the carbon on the left or the carbon on the right. Doesn't matter. One will give you one isomer and one give you the other, the enantiomer. So that's a fairly simple approach there. And the reason that the bromide ion does not attack is because water is in massive excess to the bromine. My guess is that you will get minor product, very minor products where where you get a dibromide, dibromo molecule, but most of them are going to be the halohydrins because of the massive excess of water. All right. Let's muddy the water some more with some regiochemistry. If regiochemistry becomes a problem if the alkene is asymmetrical. And in this case, we have a phenyl group on one end and two hydrogens on the other end of that alkene. So we can get a mixture of constitutional isomers where we have the hydroxyl. The hydroxyl is closest to the phenyl group, is the major product, and bromine is the minor product closest to the phenyl group. Why is that? Okay. Well, as the bromine approaches that alkene, it's going to be the nearest bromine is going to become electron deficient and form the bromonium ion. Right? That step is the same for any of the isomers. Then which one, now that you have water in excess, which one is it going to attack preferred? It's going to attack the more positively charged carbon, which is the one that's closest to the phenyl group. So that will put the bromine on the terminal carbon and the hydroxide on the phenyl carbon. All right. There's another problem that arises when you have a terminal alkene, that you can get a rearrangement. This carbocation rearrangement, remember, it moves the carbocation as an intermediate step over to the more substituted carbon. That's the more stable. So that's why the hydroxyl then is placed on that carbon. What if you don't want it on that carbon? What if you really would rather have it on number 2 carbon? Well, that's where oxymercuration comes in. All right, let's see. Here we go. So we have this mercury atom, which has an acetyl group on one side and an acetyl group on the other side. And this is in, since we want to add the hydroxyl, we got to have water in there, but we want to control the amount of water. So we use tetrahydrofuran as a solvent. And this is a two-step reaction. Once you get the hydroxyl where you want it to be, then you got to detach the mercury leaving group from your atoms. That's what the sodium borohydride and ethanol will do. Okay, so the mechanism looks like this. It's fairly complex, I'll admit. So we form this is a ring structure. This chapter is all about forming rings as intermediates. So the electrophilic addition, puts the mercury across that double bond. Now the more positive carbon is next door to the tertiary carbon. It's not on the tertiary carbon. We've eliminated the possibility for rearrangement because we're not going through a carbocation step. So we don't allow for rearrangement. So now the water can attack that positively charged or slightly positively charged carbon and put the hydroxyl where we want it. Once it's there, then we have to reduce it with sodium borohydride and remove the mercury, the acetyl mercury group. We've already broken the bond to get rid of one acetyl group, and now we're going to take the mercury acetyl group, and that'll be your leaving group once we go through the reduction steps. And I think it's so complex, that's why they just put 3 arrows. It probably takes several steps, and it's probably beyond what we want to accomplish. Is just to describe that we can put that hydroxyl group on the carbon we want without rearrangement if we use this technique. Now, the problem with reduction with sodium borohydride is that the process itself, it replaces the mercury group with a hydrogen, but it also scrambles up the stereochemistry. All right. Let's see. Yeah. So if we have this unbalanced or asymmetrical alkene, then we're going to get a mixture of enantiomers. And that occurs during the reduction step. All right. What if we use oxymercuration on an alkyne? Well, what that leaves behind, we still put the hydroxyl where we want it, on the second carbon. But we also produce an enol, which is very, very unstable. So it tautomerizes to the keto form. Right? So we don't get an alcohol on the, we get a carbonyl group instead, which, if that's what you want, fine. You know, we've created another ketone. There's for this particular molecule, you've got an aldehyde on one end of the molecule and a ketone on the other end. All right. Just when we think we've got it figured, another fly in the ointment. These are just more examples. And this mercury the key to this is not the mercury with the acetyl group. I mean, that does accomplish the reaction, but it's the mercury that forms the 3-membered ring. That's where we focus our attention. And depending on the reaction environment, we might simplify that molecule. In that first example, mercury 2 chloride or mercury 2 sulfate in sulfuric acid. All right. Also, if we have internal alkynes, right? The first example we had was a terminal alkyne. But if we have an internal alkyne, we can guarantee the formation of a ketone. Now, the ketone in this situation is going to be closer to the terminal end than the major product is going to be closer to the terminal end. We get a mixture. A mixture of ketones will be produced. And the mechanism must not be that important because there's no slide on it. So we're going to move on. Now, if you, instead of water, if you use an alcohol like methanol, you can form an ether, right? And it's a similar mechanism. Instead of putting an OH group on that, on the desired carbon atom, now we put an ether group. And it occurs through a similar mechanism where the oxygen attacks the more slightly positive or electron deficient carbon with its lone pair electrons. All right, what if we do this? Okay, we got ethanol. We're going to produce an ether. All right, we're going to produce an ethyl ether on the second carbon from the terminal. That's what I'm guessing. Did it tell us to draw the mechanism? Oh, yeah, detail mechanism. Okay. So we got to form the, what is that called? Did they name that mercuronium ion? I guess. If we're consistent, bromonium, chloronium, mercuronium ion. That's what I think it is, and I'm sticking to it. So then the oxygen from the ethanol is going to attack the more electron deficient carbon, and we get the ethyl ether, and then we have to do the workup to get rid of the mercury. And when we do that, that puts the that puts the ether on the second carbon. How about hydroboration, BH3, boron trihydride? Remember from general chemistry, we were talking about, or hopefully your instructor was talking about, Lewis dot structures. When we did boron trihydride, it was an example of a deficient boron, an octet deficient. It's only got 6. So it'd be trigonal planar. But this is in tetrahydrofuran, and it's a 2-step process. So what do we want to end up with? Well, in this case, we want an anti-Markovnikov addition of the hydroxyl. We want the hydroxyl on the terminal carbon, not on the second carbon. And if we use boron trihydride, then we're going to get what we want. Now, does that work for? Okay. The rule actually says that the hydroxide is going to end up on the more substituted carbon. Anti-Markovnikov puts the hydroxyl on the lesser substituted carbon of the alkene or the cycloalkene. So the cycloalkene in that bottom step, we're going to get the hydroxide on the less substituted carbon. Unfortunately, we get a mixture because we do have the potential for creating a chiral center. Let's see, are those superimposable? Non-superimposable. Let's see. The left one, methyl group forward, hydroxyl back. The one on the right, methyl group back, hydroxyl forward. What if that's a meso compound? If we flip it over, yeah, that's meso. And trans 2-methyl cyclopentanol. If you just flip one of them over, right, take the backside and just rotate it toward you, then they're superimposable. Okay. All right, what is this thing trying to tell me? We've covered two reactions that serve to add water across carbon-carbon double bonds or triple bonds. Acid-catalyzed hydration, which proceeds through carbocation. Okay, we've done that one already. Oxymercuration, which proceeds through a cyclic mercurinium. Mercurinium, there it is. Mercurinium ion, I was close. Avoiding the carbocation rearrangement. Both of these reactions add water in Markovnikov fashion, in which the OH group is one that is better able to stabilize the positive charge. And then neither of these reactions is stereospecific. In each case, a mixture of stereoisomers, both syn and anti-addition, are produced. Now that I'm looking at that again, that bottom one, if I rotate it like that, no, they're not superimposable. That's my mistake. They're not. So those are two enantiomers. That's what they are. Hydroboration adds hydrogen and oxygen to the alkene anti-Markovnikov. Okay, so there's your option. If you want to put the hydroxyl on the less substituted carbon, use hydroboration. All right. So why does it do that? Well, the molecule, we write the molecule as BH3, but it actually exists as diborane. At least oh, and it goes back to the stability of the boron because it doesn't have an octet. So it is an electrophile since it's missing 2 electrons in its octet. So the diboron arrangement tends to stabilize it, but it still has a boron that those bonds can be easily broken, and you still get the octet deficient boron. So that's what attacks. Okay, hold on a second. We're using tetrahydrofuran. Provides some stability. Okay. Anybody know what tetrahydrofuran is? That's an oxygen. It was, let's see, I think here and here, like that. That's furan. If we hydrogenate that one, this one, and do the same thing for this one, that's tetrahydro. because with the double bonds, we already had one hydrogen here and here and here and here. We just add 4 more hydrogens across there, and now we have THF. But we still have, let's see, 1, 2, it'll be like that. All right. So when we write a mechanism, we simplify things as far as we can to make it more understandable. So we're going to, when we draw the mechanism, we're going to only use BH3 as the electrifier. And we form partial bonds between one of the hydrogens and a carbon and the boron and a carbon. This is an intermediate step. And when it's during the reaction and the partial positive charge is better stabilized on the methyl substituted group, the more highly alkyl substituted group. And notice that what we're trying to show with the length of those bonds is that the bond here between hydrogen and that carbon is weaker. And the boron attracted to the other carbon is a shorter, stronger bond. So why does it do that? Well, let's see. 2 possibilities, actually. This is a partial mechanism, right? That would give us the boron on the least substituted carbon. And then this mechanism says that, well, what would happen if we tried that with the boron on the more substituted carbon? You get steric repulsion. We're blaming it on steric hindrance of that methyl group. Okay, so that's why the boron wants to go to the least substituted carbon. All right. Production of alkylborane, dialkylborane, and trialkylborane. All right. So we saw that example in previous slide where the boron attacks the least substituted carbon. Okay. And then why do they call it an alkylborane is the one we were looking at before, wasn't it? Yeah, alkylborane. Oh, okay. I see. I missed the R group, right? If you put an R group on the boron, in other words, now that cyclopentane and its substituents become the R group for let me see, you can see my arrow. That R group right there was this bunch right here. So we're saying that now we're going to take that substituted boron and it's going to add to another cyclohexene. And then it's going to add to another one. So we get a trialkyl borane out of this whole mess. What does it look? All right. Did I lose anybody on that one? I almost lost myself until I realized that we were going through three of the same reactions. Because if you look at boron like this, like that, and then you just substitute your R groups right there. We went through one reaction for that one, second reaction, third reaction. Now that boron has three of those groups attached to it. Okay. And to save space, I think that's why they just called it R. So in this slide, we've got those R groups, which are identical to the one that's shown. And what that does is it makes that boron more stable. The diboron that is now the leaving group. And we substitute a hydroxyl in there for that one. And that's one way that we can, well, actually, it happens on all three of them. Three equivalents of alcohol are produced. If we treat our solution with hydrogen peroxide, right? Are they going to show us a mechanism? Yeah, here we go. All right, so the hydrogen peroxide gives us a nucleophile, right? Let me go back and look at the environment. Hold on a second. All right, it's basic. Basic environment with hydrogen peroxide. So what does that do? Well, the base produces a hydroxyl ion. The hydroxyl ion strips off an acidic hydrogen from the peroxide. Now that makes the nucleophile, the peroxide ion, and it forms a bond with boron. And then the bond with boron breaks, and we get an alkyl shift. 1,2 alkyl shift. To form a borate ester. Okay. I don't see that in the mechanism. Huh. Sorry, it escapes me. All right. If I give you a question like that one in the test, just call me on it. Because if I can't figure it out, then I can't expect you to figure it out. So let's just focus on the overall reaction. We get three equivalents of alcohol out of this because there are three of those groups attached to that one boron. All right, what would happen with this one? All right, we're going to hydroxylate it after we form the trialkyl boron. All right. All right. There we go. Okay. And where's the hydroxyl going to go? It's going to go on the least substituted. Okay. What happens when we try to use boron trihydride and an alkyne? We get addition of the hydrogen and the borohydride on the same side of the alkene that's left over, simply because we formed the three-membered ring. I'm thinking that's the reason for it. Now I'm looking for the mechanism. It didn't show us the mechanism. Oh, that's cheating. Okay, we can use. All right, I think we're looking at a problem here. We get a mixture of products when the carbon-carbon double bond reacts with further boron trihydrides. We get a mess, a mixture of products. So the next slide is saying this is how you avoid that. What you need is a bulkier alkyl group on the boron. Diazoamyl borane. That's a mouthful. And we we attach the boron there to the terminal carbon on that alkyne. And the result of that one gives us a terminal hydroxide on an alkene, which is an enol. It's very unstable. It tautomerizes into the aldehyde. So if we use this procedure on a terminal alkyne, we can get an aldehyde out of it. That's what I get from this picture. These are other useful boranes. Dichlorohexylborane. Not only excuse me, it has very bulky. So diazoamyl borane, dichlorohexylborane, this heterocyclic, not heteros, yeah, heterocyclic bridge. This is a bridge cyclic, nonane, abbreviated 9-BBN. Can't imagine why they want to do that. Or other possibilities. And they're useful because they're bulky. Okay. Okay. So now we're going to look at the retrosynthetic approach. So if we want to end up with this cyclopropane on the left, how do we get there? Well, we need to have those groups sticking out to be on the same side of the molecule, right? They need to be in the Z position. And then if we attack it with the carbene made from diazomethane, then we can get back to that cyclopropane group. Just have to watch out for the explosions. All right. Another possibility. Well, notice we're focusing on the epoxide and which way are the attached groups to that epoxide. One is pointing back, one is pointing forward. That means if we're going to make that epoxide from an alkene, those groups must be cis to one another. Trans, excuse me, not cis, trans. They have to be trans to one another to give us the outcome that we want. So that's the focus here. And we want to preserve the stereochemistry. Right? That's why we would, rather than using the carbene, we would use the metachloroperbenzoic acid. It would preserve the stereochemistry. All right. Um, these are examples that we could go through if we had time. All I've got here is an explanation. Okay. In the absence of a nucleophilic solvent, molecular bromine and molecular chloride will add anti across the carbon-carbon bond of an alkene. Okay. That's because they go through the bromonium or the chloronium intermediate. They have to add anti. If we're forming a halohydron, if we have a nucleophilic solvent like water, then we can form a halohydron from uh, in this process. That's the second one, second example there. We can form either a singly substituted alkene, or if we have excess of the halogen, we can completely halogenate the alkyne. So it doesn't show the one equivalent stage. It only shows you the two equivalents there to form the tetrahalide. I wonder if that's how they form Teflon. Right? Polychlorinated. Yeah. We'll probably look at that in 24, chapter 24, when we look at polymers. All right, where does this get us? Oxymercuration and hydroboration. They add water across a carbon-carbon double bond or a carbon-carbon triple bond. Right? And that doesn't help. That just tells us where to look for them. Oxymercuration results in a Markovnikov addition of water, where the hydroxyl is on the more substituted carbon. Let's see, convert an alkene to an alcohol or an alkyne to a ketone. It's possible. So we're just running down the list of things you can do with these reactions. And I didn't keep track of them up here because there's not enough. I didn't take the. Actually, I should have put electrophilic addition will come in two stages, either through carbocation formation as an intermediate or through cyclic intermediate. Yeah. All right. Catalytic hydrogenation. You know, there was a catalytic hydrogenation question on the exam, and we had not covered that, had we? Do you remember that one? Platinum and hydrogen? Yeah. Okay. So I think most everybody got it. What this does is it adds hydrogen across the double bond and makes a single bond out of it. And a catalyst is required in order to do that. Solid catalyst, in this case, palladium, platinum will work. Let's see, what else? Palladium, platinum. Those are preferred ones. I imagine you can put a little nickel in there too, but I think platinum, palladium work best. At least that's what they use in your catalytic converters in your car. But it's not just hydrogenation that you're doing in your exhaust. All right. Hydrogen is not electrophilic. So the mechanism has to differ from the ones we've seen up to this point. Dihydrogen, if hydrogen approached the pi electrons in a double bond, I don't think that the electron repulsion would be sufficient enough to make one of the hydrogens deficient, right? Because it has no more electrons left over. I mean, you try to push one electron away from a proton, and you can't do it. So I think that's why the catalyst is required. So this is what it looks like, right? First, you got the platinum, palladium. I was right. There's nickel or nickel. Nickel's probably cheaper, or maybe you used alloy of the two. I know in your catalytic converter, the ceramic matrix is coated with platinum palladium alloy. So the hydrogen atoms are absorbed onto the catalyst. So what that tells me is that hydrogen-hydrogen bond must be broken. You have to break the bond. And that makes the hydrogens reactive. Now they can be absorbed. The alkene is also absorbed onto the metal surface, and the carbon-hydrogen bond forms, and the pi bond breaks. And when it does, it makes a second carbon that is, let me see. Let me get closer so I can see what I'm doing here. So one hydrogen, okay. And then the other hydrogen has its electron. I wonder if this is a homolysis or a heterolysis. I bet this is a homolysis, where the pi bond is broken, where one electron goes one direction for one hydrogen and the other electron goes the other direction for the other hydrogen, because those hydrogens have one electron apiece anyway. I think that's what happens. This is an example of homolysis. Okay, maybe I should have clicked and gotten this information down. Let's see. This is a heterogeneous catalyst. You remember that from general chemistry, simply because the reactants and the catalyst are in different phases, right? Gases versus solids. Oh, I should have been clicking because it describes it as we go. All right. Pi bond breaks. Okay. One hydrogen encounters an absorbed alkene, and the first two carbon-hydrogen bonds are formed. It doesn't give us the details. Yeah. Left it up to the instructor to suppose something. Okay. All right. So I'm saying it's homolysis, and I'm sticking to it. Catalytic hydrogenation of alkynes. Poisoned catalysts. So the carbon-carbon triple bond of an alkyne can undergo catalytic hydrogenation because it contains pi bonds. Okay, yeah, that I can see where that would happen. The alkene is produced is susceptible to catalytic hydrogenation again So it's in the vicinity, so it can undergo hydrogenation just like the previous alkene did and produce alkane products. But it's going to produce a mixture of both alkenes and alkanes. You can control that by using excess hydrogen. Or the other way, there are two other ways you can do that to control and stop the reaction at the alkene rather than letting it go all the way to the alkane, is control the amount of hydrogen that's added so that you're controlling it by stoichiometry, or you can poison the catalyst. That is, add something to the surface of the catalyst that will restrict its ability to further hydrogenate the alkene. And quinoline is one example. It slows the reaction down, obviously, and allows you to more exactly control the reaction itself. Lindlar catalyst, palladium deposited on calcium carbonate and treated with a small amount of quinoline and lead salt. Okay, so that's one example. You know, it just occurred to me today. We like to think of science as very logical and experiment driven. And you should be able to predict the outcome of reactions. But there's a limit to that. But the limit is not as strict for inorganic chemistry as it is for organic chemistry. Organic chemistry is more akin to following a recipe and cooking a cake than it is theoretical. And that's just my opinion. That's what I see when I look at all this mess. Now, trained organic chemists might see some logic in all this, but it still escapes me. It's more practical outcomes that we're looking for. And then we try to explain them. Okay, so if we use this Lindlar catalyst, then we can stop the reaction at butene 1,4-diol in this case. We can stop it at the ene. Palladium, barium sulfate, and quinoline is another possibility. And the addition here is in syn fashion. So it produces the cis isomers. All right, so if we want to, what are we trying to do here? Oh, we're using things that we've studied already and try to create from this phenylbromine or benzyl bromide, excuse me, benzyl bromide, because I missed the carbon. There's a benzyl bromide. Yeah, yeah, bromine attached. So that's a benzyl group, not a phenyl group. And then we want to produce phenylheptuene out of this. So we're going to have to form a carbon bond. And not only that, we have to form a carbon-carbon double bond. All right, so we're gonna have to extend the carbon chain. So if we work backwards, right? If we draw this squiggly line and break the bond there after that benzyl carbon, then we can get to that place from the bromide. But that means, let's see. Oh, okay. We're going to use a uh, nucleophilic attack with an alkyne. And the alkyne has the 1, 2, 3, 4, 5, 6 carbons on it. And then we're going to hydrogenate that one under controlled conditions to give us the double bond. But in order to get there, we have to add it um, to the bromide. Yeah, there it is. SN2 reaction. And we've got to form um, yeah, we've got to strip a hydrogen off of that alkyne in order to make it reactive. And then it will attack the benzyl carbon, and the bromine is the leaving group. Okay, so that establishes the carbon-carbon bond extension of the chain, and then we hydrogenate it in order to um, give us and we have to use a poisoned catalyst in order to hydrogenate that alkyne to an alkene. Otherwise, it'll go too far.